Hi everybody, welcome to the lecture on the downstream processing in biotechnology. Today we will talk about the crystallization. Crystallization is the main separation process. So I would say that the product should be the pure solid form. Crystallization may be defined as the phase change that with crystalline or solid product is obtained from solution. Mostly we start with clear solution or homogeneous solution, like from sugar. That's why we crystallize the sugar crystal from the syrup, for example. That's why in the starting material is clear solution or homogeneous solution. And then we would like to separate or remove out the solute that dissolve in solvent like sugar dissolved in water. Right. Mostly the crystallization is the final purification or polishing process from the fermentation product. In this example for the biopharmaceutical, biochemical, including antibiotic, amino acids, organic acids, and vitamin C are market in the form of crystal, in the form crystal. And also after we crystallize, it can be used within downstream processing for recovery and concentration of components from liquid phase. Mostly, crystals are often achieve very high level of purity. If we would like to get the pure product, the crystallization is one choice for that case because we can produce high purity, it's high or greater than 99.5%. 99.5%. That form the original solution or homogeneous solution. After crystallize, there are two phase slurry or magma. We have after crystallization, we include solid phase and liquid phase. We call it the slurry phase or magma. There is a solution called mortar liquor. That include the solid crystal and mortar liquor. Mortar liquor includes solvent and solute at saturated state. After we crystallize, we get slurry or magma. The next step, you have to separate solid or crystal of the solution. We can utilize the filtration, centrifugation, and then we wash and dry prior to packaging. And the main advantage of crystallization, the first one is the high purity, and another is that we can carry out at low temperature. This can minimize the thermal damage and the especially in bioproduct. There are some thermal sensitivity like protein, amino acid, antibiotic like this, because crystallization is preferred because it operates at low temperature. Okay, it's safe for the product that's sensitive to the heat. For this slide, I will show you an example of the bioproduct in the crystal form, right? The first one example. This is the example of monosodium glutamate or glutamic acid. This is the derivative form of glutamic acid. This is more common used like amino acid and also like Ajinomoto, something like this. You can use this as the food additive. You can use this as the feed or precursor for the pharmaceutical or drug, for the powder, like for something like this. Another one is sucrose crystal. This is sucrose crystal. It's the most common sucrose crystal was sugar. From sugar cane in Thailand is the very famous. We produce the sucrose from sugar cane. And then the next one is L-histidine. L-histidine is the amino acid, like glutamic acid, amino acid. This is the crystal form of amino acid. Amino acid is the derivative or it's a building block of amino acid. That's like bonding amino acid to get the protein, something like that. It's the small molecule of the protein. It's the glutamic acid. This is three examples of the biomolecule or bioproduct in terms of crystal form. Another property important is shape and size. shape and size of crystal is also important after you crystallize. It's also important when you separate the crystal from solution, the crystal from liquid. It's important. The crystals are composed of molecules, atoms, and ions arranged in orderly, repetitive, three-dimensional array or space lattice. This is when you study the chemistry, basic chemistry in the solid state. That's like in solid state, in molecular species, lattice, something like this. For a given material, that's out to the angle between the crystal. Phase remain constant. The space lattice allow for variation in relative size of phase. Accordingly, the variation in crystal habits may be observed between individual crystals of the particular substance. For this example, we give you an example of the same crystal with different inhabit. This is the same shape, but different habit. This for rod-like shape. This is maybe shorter. Then this is a long rod, and this is a shorter rod. This is maybe precise, but all of this is the same morphology. This shape, this habit is also impact. That's right. Effect or impact to the downstream processing, like after you crystallize, is maybe to separate solid liquid. It's also effect for this. There are many factors that influence the habit, like such as solvent. We use solvent to crystallize, or the impurity present in the solution, temperature, pH. That's also affect the rate of crystal growth. The most mechanism that affect the habit, different habit, is the crystal growth. And we talked to about the crystal growth for later. The easy which crystal to recover from magma, it also depends on the shape and size. For example, crystal with chunky or compact habit are easier to filter, centrifuge, wash and dye than long habit. For example, if we would like to separate long and short, the shorter is easy for separate, for this case, for separate. It's maybe it is easy to separate. A plate is not difficult to separate also. For this case, the dendrite or twin crystal are easily to broken. Flat crystal are difficult to separate from each other. For example, right? This is a long rod, short rod, this is a plate. For this case, it easier for separate. It's difficult. This is difficult also. For example, right? Okay, the property of crystal. There are main effects, right, for the bulk density. Solid 4 characteristics that I show you, right? The plate is difficult to separate. Long rod also difficult to separate. Short rod is easy to separate, like this. The moisture content, caking property of the solid, less of distillation, apparent, something like this. Filtration rate, centrifugation rate. This also affect due to the shape and size of the crystal. The crystal for ideal condition. The crystal maintain constant habit and geometric proportion during the growth, that crystal horn invariant. We call this invariant because like we have the same habit but a different shape. It may be long shape, short shape, or plate, something like this. We call this invariant. Okay, if you would like to consolidate the crystal or the crystal growth, the crystal property, the crystal growth, we would like to increase the size of the crystal, or we would like to control the size, control the quality of the crystal product, which is controlled by the crystal growth. Yet I will talk to the crystal growth for later. Okay, for the property of individual crystals, such as surface area of the crystal, volume of the crystal, mass of the crystal, mostly we define this in terms of L. L is the characteristic length. So this is a characteristic strength. For example, if we would like to calculate surface area, we can express in terms of shape factor multiplied by L square. This is the surface area. Right, volume equal to shape factor. This Ka is shape factor based on area shape factor. Kv is the volume shape factor multiplied by cubic length or cubic distance, L power 3. and mass of crystal equal to density multiplied by Vc is equal to rho multiplied by this term. That's like K is the area shape factor, Kv is the volume shape factor. And we can estimate surface area volume of mass with respect to the characteristic length. What is the shape factor for this example? Okay. These two shape of the crystal, the Ka is the surface area shape factor or area shape factor is equal to the area divided by the characteristic length square, right? It's also it's La. That's right. La is the longest distance in the crystal shape. The long distance is La. Lb is the shortest distance in the crystal, like this. And also for Kv is volume shape factor. Area is divided by L square. Volume is divided by cubic L, like this. It's maybe La or Lb. This is the example of shape factor. We would like it to calculate like the shape, calculate the surface area of crystal, volume of crystal, mass of crystal, which related to the shape factor like this, and also related to the characteristic length of the crystal. We use the characteristic length of crystal because the real shape of the crystal is very varied. It's varied crystal. It may be cubic, it may be prism, it may be hexagonal, something. A lot of shape of the crystal. It's difficult to determine the real size. Okay, we can estimate based on the characteristic length L, like this. And in bioprocessing, like protein, amino acid, the crystal may be formed into the polymorphism. The polymorphism means the same chemical after crystalline. It may be formed in different form. It may be form A, form B, form C. It's more than one crystal form can generate during crystallization, but this is for the same chemical. Like for example, like alcoholic acid. Alcoholic acid is the amino acid, as I show you, right? The monosodium glutamate derivative. This is used for food additive for drug application. Like for example, this is we have at least two form of the crystal is alpha L glutamic acid or gamma L glutamic acid. This two form. This is made prism. These are long. This is the same chemical but different in crystal form. How is important? Because the different crystal form is also indifferent in product property such as solubility, dissolution rate, density, melting, color. Melting color. If you use this at the pharmaceutical application, some form is higher dissolution rate, some form is lower dissolution rate. Mostly in the pharmaceutical, we use the higher dissolution rate, okay, because it's higher dissolution rate. It will diffuse to the body, diffuse to the blood. It's easier or faster than the lower dissolution rate. This, for example, the application of polymorphism. As I did show your molecule for form A and form B. These two cases of L-histidine. We have form A. If you look at the crystal structure, we have 1, 2, 3, 4 molecules of L-histidine packed in the crystal structure. For this case, it's the same molecule conformer, but it's different in packing. This packing for form A, we have 1, 2, 3, 4 molecules of L-histidine. But for form B, it's only 1, 2 to packing. And another, right, this is for the L-glutamic acid. It's also different. For this case, it's different in packing, also at conformal packing. This is the crystal structure. This is show you in the morphology. Morphology. This form B is placed like, form A is not like, something like that. It gives you the example of the crystal form, like mostly found in amino acid and protein have polymorphism. It also affect to the application like pharmaceutical or food additive or different crystal form. It also different in the separation property. Right. And the next property that is very important, the size distribution. The size distribution means the size of the crystal. In the industrial, we cannot measure only one crystal, but the objective, we would like to get the same crystal size. But in reality, it's difficult to control the crystal size is the same, but we would like to get narrow crystal size distribution. Crystal size distribution means if we would like to measure the particle size, which is the percent of crystal, and also the size of crystal, the best particle size distribution, like this, the best particle size distribution is the wider crystal. For the good crystallization, for the ideal, we would like only this line, only one crystal size. That's right. This is the ideal. That's right. But in reality, okay, we would like to get the narrow size distribution. It maybe we would like to get like this. It's as possible. That's right. These are narrow size distribution. We would like to get this. That's right. It's better because the size is narrow. That means the size close to the uniform or close to the unity. Only one side. We cannot produce only one side in industry. Okay, we can control its narrow side, its uniform side. Is the side distribution. The technique to measure the side, there are lots of techniques. Right? The basic or the common is the sieve technique or screening technique. Another is image technique. Maybe we would like to microscope, PVM, and also we would like the scattering technique or light technique, Mathe-Sizer, Mauern, FBIM. Another technique we can use like the particle size. The first one example here I show you like the microscope or 2D image. For this case, we have the crystal and then you use the microscope to take the picture from the microscope. For this example, we can measure the size of crystal, but it is only two-dimensional. Two-dimensional. That's right, two-dimensional. If the dimension is depth to the paper or depth to this computer, we cannot do the depth. Only the width and length like this. We can measure right the size of this, can measure the size of this, but we cannot determine the length. This is for the true dimensional measurement. We can use this to estimate the growth. The growth, we use growth to control the particle size. And another technique we call is light scattering. Light scattering, we have the light source. The light source, after we apply the light source will contact with our crystal. The crystal. After that, we analyze, we get the particle size. For this case, we analyze the particle size is maybe you change the light crystal is maybe diffraction crystal, the light diffraction, thing like this, and then you can convert from the right fraction to be the particle size. Mostly we compare to the sphericity or spherical size. Like this. And then when I show you the Mauern program, this Mauern program utilize the light scatter, we can measure the particle size. Like this, the L is percent volume of size, like shown it in this slide. This is the particle size distribution. Mostly we plot between the size and percent of the crystal, And another technique we use the FBIM. FBIM also we use the light scattering. After I contact the crystal and then it have the reflection. If it's scanned across the surface of the particle. The measuring the reflectance time and determine the short length by the product of the time and laser scan speed. And then we can analyze and convert from the short length to the particle size. Right, this is another example. And particle video microscope also did for the image technique. Use the image technique like microscope is another example. And the most common in industry, like sugar industry, we use like screen. The crystal size distribution are most often this mean by the wide mix screen. For this case, we have like this screen. We have a lot of screen is different size. Crystal size is taken to be screen. Aperture, or we call this open. The open of the screen, open of screen, what the size of the open. The different skin analysis made by determine the arithmetic average aperture. For this case, we use the determine the size based on the opening or aperture size of the screen of the sieve. So for each case, we have like the rest of the sieve. For example, we have like the first one and 2, 3. For example, we have 4 screen, and the last one is no opening because it's pan, thing like this. Okay, right. If we have the solid or crystal, and then we use like the checker, we have the checker vibrate the seed. So we have the wide length of the particle, the solid that is size is less than this. For example, this is about 50. The opening for this is 50 micron, and for this is 100 micron. This is 150 micron. This is 200, for example. The sieve analysis with determine mass fraction that's retained in 50. How much the crystal retained in 50? How much the crystal retained in 100? How much the crystal retained in 150? How much the crystal one retained in the 200? 200 mean particle size of crystal that the larger size than 200 micron can retain in this sieve. The particle of crystal that the particle size is smaller than 200, it can pass to this sieve. It may be retained in this 150. If the size is smaller than 150, it also pass to this and retained in 100. If it's less or smaller than 100, it's also retained in 50. And finally, if it's smaller than 50, it's retained in the pan. Right? And then we can calculate the percent weight in each sieve. Right? Mostly for the sieve series, we use like US sieve series of the Taylor standard sieve series. It shows you like the US sieve 3 or tailor-made series. For example, US sieve number 4. For tailor-made, it's number 4 also the same. Opening size, the size of the screen that is open is the whole of the open is 4.7 millimeter or 0.1 s. In, for example, it's number 10, made number 9, 2 millimeter is opening. This, for example, is the screen analysis, is the opening of the white screen. The technique to separate the particle like is for the sphere, press, cube, powder, slip, large particle, very large particle. It depends on the direction or the location, orientation of the particle, right? This also is easy, but for this can separate by this side, this opening, this also this opening. If the cube can it's easy, but for this, it may be difficult. If the particle in this direction, okay, it can separate by the seed. But if in this direction, it cannot. That's right. It cannot. To solve this problem, the sieve we have the technique of sieving. That's right. We use the vibration technique to vibrate the particle. After the particle to change the direction, okay, we can separate. It's the technique to increase the efficiency of the screen technique by vibration. How to analyze the particle size? The mass fraction is very important. The mass fraction that's retained on the sieve. We can calculate delta W is mass fraction equal to delta M. Delta M means amount of mass of crystal retained in the sieve divided by the total mass. And then you can calculate mass density. Mass density is the mass fraction divided by the length. Length is the, for example, right? The distance or the length from this between 150. This is 100, this is 50. What does it mean? Between 150 mean amount of percent mass of crystal that retained in the sieve. 50 micron. and can pass to receive 100 micron. This is the 50 and 100. How about 150? 150 means percent mass of crystal or mass fraction of crystal that retain in 100 micron. That means the size is larger than 100, the size lower than or smaller than 150. This for example. Okay, this is delta L. So delta is mass of particle retained on the screen. MT is total mass. Delta L is the difference or increment aperture size or opening. The result we can plot linear graph against the average particle size, and then you can, this means the dominant size. Dominant size means the maximum size of the crystal. For example, right, we have the crystal of synthesis acid infractionated using series of C. The result shown in this table. For this table, we have the mass number 24, 28, 33, 1, 2, 3, 4, 5, 6, 7, 8. We have 10 C. And the last one is pan. Pan is there is no opening. That's right, there is no pore, no hole for opening. How many percent of the mass? Mass, the screen number 24, no crystal retained on this seed. That's 0%. That means all crystal can pass to the seed number 24. 0.05 gram of crystal retained on seed number 28. That means only 0.05 gram of crystal that have the particle size larger than mass number 28, smaller than 24, and 35, 1.05 gram. That means only 1.05 gram of crystal that have the particle size larger than number 35, smaller than number 28. This for example. And the last one, we have only 4.2 gram of crystal that have the particle size or crystal size smaller than mass number 200. That's right, mass number 200. Okay, the question, please plot the mass density distribution using histogram plots and plot the mass density using linear plot or line plot and determine dominant crystal. We determine mass density. Mass density, you have to calculate this. You have to calculate delta W. You have to calculate delta L. You plot the graph, you have to know average size. Okay. The first step, you have to check number of mass. For this case, you show the number of mass for Taylor series standard. For this case, we have 24, 28, 35. For example, 24 mass. This is the opening size or a screen opening, 0.701 millimeter or 0.0276 in. For 28 is 0.5S9. For 35 is 0.417. This for example. 200, 0.074 millimeter, for example. Okay, for this sample, we can calculate the total of MT. MT is the summation of all of this. Is equal to 91.2 grams of crystal. And then we have to calculate mass fraction. Mass fraction. For example, mass fraction that retain on Taylor screen number 100. For 100, the mass retained on the screen number 100 is 21.6. And then you can calculate mass fraction. Is the mass that retained on this screen divided by total. 21.6 gram divided by total, we get 0.237. This what does it mean? This means only 23.7% of crystal that retained on the screen number 100 or retained between 165. Sorry, 165. 100 is 0.147. 65 is 0.28. This is the size between 100 and 47 micrometer or 147 millimeter, 0.014, and 208 micrometer or 0.208 millimeter. The crystal that's retained between these two sheets is 23.7%, for example, and then you can calculate mass density. The mass density you can calculate by dividing delta W and delta L. Is it 0.237 divided by delta L? The difference of the length is between 200 and 147. This is made number 100. This is made number 65. Sorry. 65 and 100. 65 and 100. Okay. You can get M equal to this. And then you draw the table like this. And how about average? Our average is the average between these two sides also. Average between 208 and 147. For example, we would like to calculate the average size of the crystal retained on terracite number 28. Or 28, yes, you is between 24 and 28. 24 is 0.701, 28 is 0.589. This is its average, you get average. And then you create the table. This is the telemate. This is the aperture size or opening you obtain from this table. Like for 24, 0.701 or 701 micrometer. 28 like this. 35 like this, for example. Okay, this column and this column and delta L, the increment, the difference between 700 and this, get this. This and this, you get this. This and this, get this. This and this, you get this. For example, with the delta L, the increment side. And mass retain. Mass retain you obtain from this. Is from the form statement 0.05, and then delta W. Delta W is delta M divided by delta L. Okay. Delta M delta W is delta M divided by M total. This is 0.05 divided by 91.2, we get this. 1.05 divided by 91.2, you get this. 14.3 divided this, you get this, for example. And M equal to delta W divided by delta L. This divided this, you get this. This divided this, get this. Right. This divided this, get this, for example. And then you calculate the average L. This and this. 701 plus 589 divided by 2, you get this. 589 plus 417 divided by 2, you get this. And the last one, 74 plus 0, that's like the pan is 0, divided by 2, you get this, 32. You get all of it, and then you plot the mass density versus the histogram and the line plot. The first one, this is the size between 0 and the 0 and 74% of the density is 6.2. Look at this. And then 40, 74, 104, 1.6. This is about 1.6 multiplied 10 power minus 3. This means 10 power minus 3. Okay. Because this is like the mass density multiplied 10 power t. If we were to get this 100 multiply 10 power minus 3. This is also from 100 4 and 147. Yes, get about 3.5. And 147, 208. Yes. And then you get this the histogram. And you draw the line plot. The line plot is the average size. This and this. 37. 89 and 1.6. Is it 89 and 1.6? 3.5, 126, 176, 3.5, 178, 3.9. Yes, 3.9. For example, and then you get the nominal or maximal size LD. But you can use this data. You can analyze the data. And then you get the particle size distribution, like this particle size distribution. And also the mostly in the crystallization, we can analyze in terms of number of particle or number of crystal. You can convert the mass to the number particle from the skin analysis. Delta N is the amount of number of crystal that retain in the skin analysis is equal to delta M divided by low KVL average power 3. Because this is the crystal number density or crystal population density, you can calculate this equal to delta N divided by delta L. Delta L is the increment of size. And then you can calculate N is MT multiply delta W divided by delta L divided by this term. For example, from previous example, okay, for the next example, right, we have the salicylic acid crystal harvested from magma. Magma means the slurry is include crystal and solution with a slurry density of 120 gram per liter. The crystal are washed, dry, and side fractionated by we separate by the sieve at a lot of sieve, that's right, a lot of sieve side. The mass fraction of crystal which size between 210 and 250 micrometer is 0.14. This means like the size is smaller than 250 micrometers, larger than 210. It's about 14% by mass retained on these two things, between these two things. The density of crystal is 1.44 gram per cubic centimeter. Volume shape factor is KV is 0.55. Then you can use this data to calculate the population density with the crystal size of 230. What is this? This is the average size between 210 250. This is the average size. You can use this equation A, to calculate the population density. Population density. Okay, you know all this data. You already see the MT is empty 120 multiply delta W. Delta W divided by the delta L divided by density shape factor L power 3. You get this is N3. You get this is N3. It maybe is the term of per size and per volume. This means number per size and per volume. Okay. Or then you can change the unit or convert the unit from micrometer per liter to this is per length means cubic meter -1 and -3. It's the same. This is per length and per volume of the solution. It's the unit of the crystal size distribution. Okay, I will stop this the first lecture on crystallization. For this lecture, we talk about the particle size analysis. It focus on the particle size analysis because it's the product crystal. The particle size is very important. The particle size is indicate the quality of the crystal. Like when you talk about the sugar crystal, the uniform crystal size is preferred for the industry. Okay, we will stop this lecture and we continue the crystallization for the next lecture. Thank you.